A little while ago, I opened up an IRB console and I ran this command, which Ruby's underscore makes it really easy to see just how big this number is. It's 1 billion. So 1 billion times object.new. And I'm not the most patient, so I was doing other stuff on my computer and it came back, and about 2 minutes later it was done, which is crazy if we stop to think about it. Kind of, I was doing other things without a problem. I created 1 billion objects. And for context, so if we think about this, each of those objects, and we'll dig in a little bit into more of why this happens, but each of those objects takes up at least 40 bytes in memory. If we do 40 bytes times a billion, that's 40 gigabytes, which for context, my machine is only 16 gigabytes. So what was happening here? How come this could happen and I could keep sort of doing other things in the background? Well, Ruby has a garbage collector, and in many cases, we take this garbage collector for granted. We know we can do things like this, and the garbage collector will just take care of it. And in this talk, when we're talking about Ruby's garbage collector, we'll be talking about CRuby or MRI Ruby's garbage collector, not JRuby or Truffle Ruby or any other kind of Ruby. If you don't know what that means, that's totally cool. It's just the Ruby you're used to. So back to what was going on here. I didn't keep a reference to any of these objects, right? So the garbage collector just ran and ran and ran and let me keep creating them. And we'll go more into what GC stat does, but it's telling us how many times the garbage collector ran. So we can confirm after this command, it had run over 50,000 times. And we'll talk more about what pages mean in the context of this, but we can confirm pages are how much memory it was taking up, and we can confirm that amount of memory didn't change, right? I made these billion objects and I didn't grow my memory by leaps and bounds. And so Oscar the Grouch, one of our favorite Sesame Street characters, would tell us, go away, right? Don't pay attention to the trash. It's not something you need to be concerned with. Ruby will just run it in the background for you. That's the whole point of a garbage collected language. You don't have to think about it. But I was, like probably many of you, reading through the Ruby 3 release notes when they came out on Christmas Day, and you don't have to read this whole block of text. I know it's bad presentation form. But there is one thing at the end here, which it says, please test first, right? And so if we've done this whole thing of we're just gonna ignore the garbage collector, we don't really care about it, it's working in the background, we're never gonna be able to test new features or do a whole host of other things when we do have garbage collection issues. So today I'm gonna run through my talk, a day in the life of a Ruby object, or as the case may be, a day in the life of a billion Ruby objects. This was originally a RailsConf talk, and it's kind of been condensed and compressed a bit for this. So I took out a bit of the funny parts and a bit of the compaction at the end. But for the fuller version, as Toby was saying, feel free to come to RailsConf, or I think they'll post that longer talk eventually. And also, just while I'm here, big thank you to Toby and Pascal and Jonas and Ramon. We did a whole little RailsConf prep session, and it was really helpful for me. Okay, so my goals here are we're going to be able to better conceptualize GC related issues in the same way you might see an issue and know, this is something to do with networking or something else. My goal is that if you see a performance related or memory related issue, you could think, this could be something to do with GC. And in order to accomplish that, we'll need a much more general understanding of what GC is doing, how it's working, and the arc of object creation. So what's actually happening when we create an object? Where's that object going? When's it living? When's it not living? All of that. A little more about me. As Toby said, I'm working on a book about Ruby garbage collection right now. I blog about Ruby on my own blog, and also with Tip of the Week through Ruby Weekly. And I'm also a backend developer. And just a small plug, also, while I have your attention, I'm one of the organizers of WNB.RB, which is a new Ruby women non-binary group, where once a month we have talks given by women non-binary folks. Feel free to check us out on Twitter. Our latest events are always there. Okay, so to go back to this little snippet from the Ruby 3 release, the test first. If we look at what it's talking about, it's talking about compaction here. And so if we zoom back out to the Ruby 2.7 release, that was the one that introduced compaction. And it introduced it with a whole bunch of terms, right? Memory space, memory fragmentation, the heap, pages, copy on write friendly. What do all these terms mean? If we're going to understand it, we need to understand a few definitions. So let's walk through, kind of go back to our object and see in the context of the object what all those terms mean. So we started with a billion. Instead of a billion, let's just zoom in on one object, and we'll see that if we just open up an IRB console or something and create a new object, we'll get some address, some memory objects. But how can we access this object? We can't, right? We know if we want to be able to access it again, we would have needed to store it under some variable so we could reference it. And only then would we be able to access it again. But let's look, what was that memory address actually saying? So in order to understand that, we need to zoom out to our operating system heap, which we can think of as the memory on the machine we're running. And we're going to kind of dig down looking for where our object is. So the next level is Ruby actually has its own heap. It's going to feel a little like we're turtles all the way down, but we'll get to the object eventually. The Ruby heap contains the memory that Ruby is storing and controlling and asking for. And the Ruby heap can actually sometimes reference the operating system heap. We'll see cases when this happens shortly. And it can grow. This obviously isn't to scale, but it can ask the operating system for more memory and take up more space within the operating system. So if we zoom in on the Ruby heap itself, looking to get to the object level, we'll see that the Ruby heap is actually made up of these units called pages, where it asks the operating system for more memory in page chunks. And each page is about 16 kilobytes. It has a little header information, and then it has these things called slots. It has about 409 of them. And the slots, we finally reached where we actually store the objects. So the slots are fixed size. They're this 40 byte size we referenced earlier. They can be empty, unallocated slots, or they can have R values in them, which are Ruby values, Ruby objects. And that's where we'll store things, right? So that's where the objects themselves live. So you can see on this page, we have 2 objects and a whole bunch of slots. And if we zoom in on an R value, that's where our object itself is stored. But I referenced earlier that in some cases, the R value, the Ruby heap can have references back to the OS heap. And that sometimes happens if we have objects that are too big to store within one R value. So we only have 40 bytes. So what happens if we have a string that's too much for the R value? This visual is meant to explain it'll overflow. Instead, what happens is, and this actually happens in the case of strings, in some cases, the R value will store some external memory address and will point outside into the operating system heap for where that value is. So this supercalifragilisticexpialidocious could live outside of the Ruby heap. And an interesting note on that point is that in some cases, this means the amount of memory we'll see on Heroku or on AWS is actually larger than the size of the Ruby heap itself, because Ruby is taking up space in the operating system heap. And something neat we can actually see where this limit is for strings, where it'll store outside of R values. So to do that, we first need to look at this little formatting tip. If we use this %.23d, we can make a number take up 23 characters or however many characters. The limit for string, so here we're doing 1 million times creates different strings of length 23. And we can see if we do that for length 23 and 24, that's actually our boundary of where the string is stored within the Ruby heap and external to the Ruby heap. And you can see, or we can all see together, you can see it and I can see it, hopefully, the processing time changes by almost a factor of 10 if we're doing that 1,023 line strings versus 1,024. And this isn't necessarily a practical thing. I doubt many of us are creating 1 million arbitrary strings all the time, but just kind of a neat explanation of where we can really see what's going on with memory. And there are other cases where R values could reference other R values. For instance, if we put our object from earlier into an array here with some other stuff also in the array, what'll actually happen is that R value will reference our object, which is its own R value external to the array. And we can actually see this. So something really cool about Ruby and its metaprogramming is a lot of what's going on in the garbage collector we can see. There are ways to see it. And one is through using this object space dump method, which gives us back a JSON representation of some memory information about an object. And we'll get more into more details there. But for now, that's all we need to know. And if we dump the array, we can actually see its references. And what's very cool here is this, this memory address that ends in DA468 was actually the same as our object's memory address. So we can see it was referencing our initial object. But for now, let's get back to our billion objects and try figure out what was happening there. Well, we know we needed within our Ruby heap a page to store R values or objects. So we can put some R values in that page, but we know it was probably a lot of pages and a lot of R values. But if we kept going, we know with the 40 gigabytes, it just wouldn't fit, right? I definitely wouldn't have been able to do other stuff while it was happening. We would have quickly run out of space. So what was happening? What was the algorithm that was collecting all these objects and cleaning it up? Ruby uses an algorithm called, or Ruby's garbage collector uses an algorithm called the tricolor mark and sweep algorithm. And again, don't worry about reading this all, we'll step through it, but this is the gist of the algorithm. So we mark everything white, we transition things to gray, and then eventually to black. And so the first step, mark all R values white, great. Second, mark all root R values gray. Well, what is a root R value? These are R values that our program will always know about, that are vital to the running of the program. And so we start here because anything that's not reachable from these root R values will not be collected. Examples are VM, finalizers, machine context, global lists. Those are all root R values. That's where we start. And so to explain this algorithm and how it works, we'll need a few root R values, but we can kind of move them out of the way because we'll also need a whole bunch of other R values. And we'll need also references. So this is like in the case of the array, which we saw earlier, where the array was referencing one of the objects in it. That's what these arrows represent. And I tried in this diagram to do a broad array of different references. So we have some cases where there are R values referenced from the root, some cases where there are R values referenced from other R values. Some R values have no references at all. But let's walk through this algorithm. So we have all our R values. The first step is to mark them all white. So they're all white. We've done that. Great. The next step is to mark all of our root R values gray. Okay, mark all our roots gray. Great, we did that. The next is this while loop. While we have gray R values, pick a gray R value. Okay, we picked this gray root R value. Mark all R values it references gray. Okay, that's this highlighted one. And then mark it black. Okay, we marked it black. Again, we can step through, pick a gray R value, mark everything it references gray, mark it black. Pick a gray R value, doesn't reference anything, mark it black. Pick a gray R value, mark everything it references gray, mark it black. Pick a gray R value, the same, right? Doesn't reference anything, mark it black. And then we'll finish this loop. We have nothing more to do in our while. We don't have any gray R values left. We're done with this. All we have left are these black R values and these white R values. And what the garbage collector now does, this is kind of the critical point, is it says all of the slots that these white R values were taken up can be used by anything else. We don't care what's in there because we don't actually anymore have a way to even reference the contents there from the root. So let's get rid of them. So if we look at this in terms of our page diagram, we had all these slots. We filled them all up, right, with some of our billion objects. Then the mark and sweep algorithm came and it said, here are all these R values that aren't connected, aren't referenced by anything. Let's get rid of them. We'll collect them away and say their slots can be reused. And then we'll have these slots to reuse again. We'll fill them up with more R values. And so if we zoom out on this, we can see it on a bigger level. We can see how my computer managed to do this so easily. It had all of these slots that were filled up with R values. It needed more memory, so garbage collection ran. It said, hey, we can actually take back all of these slots. Then more objects were created and the same thing kept happening. And we know that happened so many times, right? We saw already it happened 50,000 times, at least, more than that. So the mark and sweep algorithm was really quite handy, but why tricolor, right? Couldn't we have done this with just black and white? What's the point of the gray intermediary state? It actually allows us to pause the garbage collection and to keep going. So Ruby's garbage collection is what's called stop the world, which means in order to run, it stops execution of your program, which is a cost, right? Definitely a cost. And so you can think if without this gray state, you would have program execution, and then you might have to take a really long pause for garbage collection. And if that happened at an inopportune moment, that could cause real issues in the execution of your program, right? You could be, a user could see like waiting for a few seconds or something like that, just randomly. So we use the gray state to allow us to pause and keep an intermediary state of garbage collection. So looking at this diagram, it's very clear which R values we've already looked at and which we haven't. Whereas were it just black and white, it wouldn't be clear which ones we would have to go and mark again. So instead, Ruby uses, because of this gray tricolor garbage collection, and incremental garbage collection, where it can just do these short pauses and only stop the program execution briefly. So if we go back to our object, we know we're holding a reference to it, right? So it won't be collected because we have a reference to it, a live reference. But let's combine these two ideas. What if we held a reference to our object and then we did this billion object creation and then wanted our object again? We know we would be able to get it, but would it happen that the garbage collector would just look at this object in every single one of those 50,000 GCs for nothing to ever change to it? That seems really inefficient, right? Which brings us to generational garbage collection, founded on the weak generational hypothesis, which is that most objects die young. So we can think in our Rails apps, there are lots of parts that are transient, right? Creating a web page needs a whole bunch of objects, but once the web page has been returned to the client, we don't need those objects anymore. Or we can think of a method where we might make a bunch of intermediary objects within that method, but then we'll never use them again. And so we can therefore look at the older objects less frequently and look at the younger objects more frequently. GC.start is how we kick off our garbage collection. And there are actually two optional, it can take an optional argument of full mark, which is a Boolean false or true. Full mark false means only look at the young options. And this will only happen in a minor garbage collection. This is what a minor garbage collection is. And these will happen automatically. Like I said, there just are ways to manually kick them off too. Versus if we did a full mark true, it'll look at all objects, young and old. And that's called a major garbage collection. So we now have these two different types of garbage collection: minor, which is only some objects, and major, which is all objects. And we can actually see the RailsConf talk gets more into this, but GC stat gives us statistics about our garbage collection. And it's this kind of crazy thing. A lot of these will now be meaningful, hopefully, but the ones we really care about are this minor GC count and major GC count, which is telling us how many minor GCs ran versus major GCs ran. And if we run this, if we, instead of doing GC stat of all our garbage collection, we just looked at the minor GCs, we would see there were actually 50,000 of those and only 4 major garbage collections. But looking even more, these 4 major garbage collections had actually happened just in loading IRB. So all through our billion object creation, we never once did a major garbage collection. And we can see our minor GC count, just to confirm, started really low and grew to over 50,000. So what was happening here is the object became old, so it wasn't in any garbage collections. We didn't need to look at it all 50,000 times because we were just doing these minor garbage collections. And we can actually see this if we go back to our dump method that we had defined earlier. We can see age in the results of dump. So let's look a little deeper into some parts of dump. It'll give us the address of the object, the type, the class. What's neat here is we know our class is object, right? And so if we dumped the object class itself, that memory address will be the same as the dump of our object's class because it's of type class. We'll see again that its size was 40 bytes. And this flags is where we'll keep whether it's old or not, only when it's old though. So if it is old, it'll have a flag for old. So we can define a little check if our object is old, and can create this little count GC until old to actually see that it's happening and see that at some point our object becomes old. So we make a new object, we set GC count to 0 while it's not old, keep manually running the GC and increment our GC count. And if we run this, so manually run the GC. If we run this, we see that we get 3 garbage collections until it's old. And this is actually, the age of an object is actually stored in the RVALUE itself in 2 bits. So every time GC runs, our age will increase a little bit or binary arithmetic here until it gets to 3, and then it'll be an old object. And that's really an overview of generational garbage collection. So just to recap all the things we talked about, again, this was slightly condensed, but the RailsConf recording will have even more content here. We went through the structure of the Ruby heap. We went through tricolor mark and sweep algorithm. We went through incremental garbage collection and generational garbage collection. And we got to see or my computer at least, run and create a whole bunch of objects. So thanks again, really, to everyone in the Berlin Ruby group, especially for helping me with this talk. As Toby mentioned, and as I mentioned, I'm working on a book about this. The best way to get updates on that are any of these 3. There's a newsletter I have at Button Down Email where I'll definitely keep emailing blog posts. You can find me on Twitter, and on my blog itself, I'm doing a garbage collection deep dive series. So you can definitely follow along there if you want.